Students, in this video I am going to teach you method of successive approximations. So in this category we are having three methods. One is successive substitution, another one is resolvent kernel method, also known as Nyman series, and successive approximation method. So these are three methods. So here, to start this method we need some definitions like iterated kernels and then resolvent kernel. First, so as ODE are solved by Picard method, because we have already seen in numerical methods, an ordinary differential equation, basically an initial value problem, can be solved with the help of Picard's method to get approximate solution. Similarly, linear integral equations of second order may be solved using successive approximation method. Fine. So this is just like a parallel method. In ODE we are having Picard's method. Similarly, in linear integral equations we are having successive approximation methods. First recall iterated kernels. So since we are having two types of equations, one is Fredholm integral equation, another one is Volterra integral equation. So now for Fredholm integral equation of second kind, this is the equation, Fredholm integral equation of second kind. This is the iterated kernel, where k1 is nothing but the exactly equal to the kernel kxt, and then next kernels like k2, k3, k4, k5, they can be evaluated with the help of this formula, which is knxt is equals to a to b. This a to b is exactly same as the limit of this kxz kn minus 1 zt dz. This is z. Fine. And z is the intermediate variable. After substituting the limit with respect to z, which are nothing but a to b, finally we will get a function of the form x and t. Fine. This is, you can interchange also. For example, here kxz, here is zt. So when you interchange these two kernels, so here you may also take kn minus 1 xz, here is kzt dz. So they will provide you same answer. Fine. Here n is 2, 3, 4, 5, 6 and so on. Similarly, for Volterra integral equation of second kind, this is the Volterra integral equation of second kind. Its first kernel is k1xt is equal to kxt, which is as it is same, and then knxt is given by t2x kxz kn minus 1 zt dz. Here the limits are x to t2x. Fine. These are, so here upper limit is as it is same, however lower limit a is replaced by t. Again you can interchange these two. So kn minus 1 xz kzt dz. Again z is the intermediate variable. So these are the iterated kernels. Now second is the resolvent kernel. So for Fredholm integral equation of second kind, this is the equation. Its solution in the form of resolvent kernel is given by this. Here f of x, y of x, f of x as it is, lambda as it is, integral as it is. In place of kxt now we are having resolvent kernel rxt lambda, and in place of yt we are having known function ft. Fine. And we have already shown you that this is the solution of this equation when we have discussed this resolvent kernel. Similarly, the Volterra integral equation. Volterra integral equation is this. Its solution in terms of resolvent kernel is given by this. So yx f of x plus lambda, in place of kxt we are having resolvent kernel, in place of yt we are having ft dt. So you can find out the solution. So this is now here, this is solution of Fredholm integral equation of the second kind. Fine. By successive substitution. So we have this method in the form of this theorem. What is the theorem? Theorem says that this is the Fredholm integral equation of second kind, and suppose that kernel kxt is not equal to 0 is real and continuous in the rectangle R, and this rectangle R is defined by this: x varies from a to b, t varies from a to b, and also magnitude of kxt is less than equal to m in R. That means kernel is bounded. This kernel is bounded and non-zero in this rectangle. Similarly, f of x is non-zero, is real and continuous in the interval I for which x varies from a to b, because this is a function of x only. Again, this function is bounded in I, interval I. So again, just like kernel, function is non-zero and bounded in this interval I. Fine. And continuous also. Just like here, function is non-zero and continuous and bounded in this interval. Lambda is constant and satisfying this property. Magnitude of lambda is less than 1 by m into b minus a. If this equation satisfies these three properties for kernel, function and lambda, then we can say that one has a unique solution, which is given by this series. So this is given by this series. Y of x is equal to f of x plus lambda a to b kxt ft dt plus lambda square a to b kxt a to b kt t1 f of t1 dt1 dt and so on. This series is uniformly convergent series. Absolutely and uniformly convergent series. Fine. So now we have to prove this. So let us see how to prove this. So here consider the Fredholm integral equation of the second kind. This equation. Here you will see that here we have y of x, here we have y of t. So just replace x by t here. Fine. So if you replace t by here, then here will be yt, here is f of t, here tt. So to avoid this tt, because here is t again. So to avoid this, first we will change this t by t1, so that here we have t1. So rewrite equation number 1 as this equation. Just replace t by t1 here, and now replace x by t here. So we get this equation. Now substitute this yt from here in equation number 1. So we get this equation. Fine. So y of x is equal to f of x plus lambda a to b, this kxt, and now in place of yt we have this. So we have substituted here. Now separate the terms. So we get this equation: f of x plus lambda a to b kxt, this ft dt, plus lambda into lambda square, integral a to b, this kernel, multiply by this integral a to b kt1 yt1 dt1 dt. This is equation number 4. Fine. And we will proceed further again in the same way. First replace x by t here, so we get this equation. So again rewrite third equation as this. You will see here what is third. Here equation number third, here replace this equation by now t2. In place of t1 we are having t2, because we have to proceed further, because here you will see that here we have yt1. So again we have to substitute yt1, just like yt. जैसे हमने यहाँ yt substitute किया था, अब हम yt1 को substitute करेंगे. So to do that, first interchange this t1 by t2 here. So this is the equation number this 5. We have replaced t1 by t2, and now substitute this yt1. Replace this t by t1 here, and now replace this yt1 in that equation. So we get this equation. So in place of yt1 we have this integral in equation number 4. Fine. Following the same way, we and simplify this, so we get this equation. Fine. So now proceeding likewise, now we have to substitute yt2, then y33, y4t4 and so on. We get this type of series, which is f of x, y of x is equal to f of x plus lambda a to b kt ft dt plus lambda square. From here we have f of x, this term, so they are the terms plus and so on, plus just like here we have third order term. So when you're proceeding, so we will somewhere we will get nth term. So this is the nth term, this is the generalization of this, इसका जनरल टर्म है. So lambda n a to b k x t, a to b k t t1, a to b k t1 t2 and so on. If you will see here, if here is 3, so here we have 2. So if we have here n, so we will move up to tn minus 1. So this will be the last integral in this way, 1 2 3 and then n minus 1th integral. So this is n minus 1th, this is nth integral, sorry, when 3, so we are having 3 integrals, 1 2 and 3. Similarly when n, so we will have n interval. So this is the nth integral, nth, a to b k tn minus 2 tn minus 1 f of tn minus 1 d n minus 1 dn minus 2. Sorry, this is the actually the this term, because this is here we have f. Fine. So here we are writing this term. So here we have 2, so 2 integrals. Here we have n, so n number of integrals. So we are writing this integral. Fine. So this is the generalization of this. So we have written here final this plus the term of this order which involves yt. So this is the term here, yt is involved. So here is, when here is 2, here is 3, when here is n, so in the next interval we are having n plus 1. So we are not writing this part, rather than we are writing rn plus 1. This is the remainder term, where rn plus 1 is what? This is the generalization of this term. Here is n plus 1. If here is 2, here is 3. Similarly here is n, so here we have n plus 1. So now we are having n plus 1 integrals, a to b k x t, a to b k t t1, a to b k n minus 1 tn, yt and dtn dt1 and so on, just like this. So this is the generalization of this. You can simply rewrite with the help of this equation. Simply, here is 3, here is n plus 1, here is kxt, here is tt1 and so on. When here is 3, here is t1, here is 3, here is 1. That means n minus 3 minus 2. Similarly here is n plus 1. So obviously n minus 1. Minus 2 कर देंगे यहाँ से जो भी होगा. So minus 2, n plus 1 minus 2 we will give you n minus 1. Then t2. So tn एक को ऐड करेंगे. Then ytn, dtn and so on. So this is the equation. Now let consider the infinite series in view of equation number 8. In view of 8. Fine. So this is the infinite series. So we are writing this equation. And then after writing two terms, we can just simply write dash dash dash. So that we are having infinite series. Now our purpose is to show that this series actually uniformly, absolutely and uniformly converges in the interval I. Fine. So in view of the assumption 1 and 2, each term of the above series is continuous. This is our assumption. So obviously this series is basically continuous in interval I. Because each term is continuous, so their addition will be continuous. So this series is continuous in I, provided it converges uniformly. Fine. So now the next part is to show that, now let un denote the general term of this series. So we are writing the general term of this series here. If you will see that is general series, general term. What is the general term? General term involves ft. Here is ft. So this is the general term. So we are writing this term. So this is the general term. unx is equal to lambda raised to the power n, a to b kxt, a to b k t t1 and so on, a to b k tn minus 2 tn minus 1 f tn minus 1 dtn d. This equation actually is inspired from here. This or this. This is the general term from here. Lambda 2, so we are writing lambda n. A to b kxt, a to b. So this term, this general term is taken from the series. Fine. Involving f of t. So now taking the magnitude both sides, so this equal to magnitude of this right hand side. Now if you take, so you can separate term by term. So magnitude of lambda raised to the power n, this, then magnitude of this kernel, magnitude of the second kernel, magnitude of this kernel, magnitude of f of t1. But what is magnitude of f of n tn minus 1? This is nothing but n. Fine. Magnitude of kernel. What is the magnitude of kernel? How many kernels are there? Total 1, 2, 3, n. And the value of each kernel, magnitude of each kernel is m. So m into m into m, m raised to the power n. So finally we have to solve the integrals a to b, a to b, a to b, and dt and dt1. How many these integrals are there? Total n number of integrals. Fine. So when you solve particular integral like this, a to b dt, what you will get? You will get b minus a. So from here, when you have taken this as a constant, because magnitude is nothing but m, you have taken this and outside, similarly taken this outside, so ultimately you will have only integral a to b, a to b, a to b. How many integrals are there? Total n. And from each integral you are getting this term. How many integrals are there? N. So this will give you b minus a raised to the power n. टोटल n इंटीग्रल है, हर इंटीग्रल से एक b माइनस ए आएगा. So b minus a raised to the power n. So after solving this we get this. Fine. And we have used assumption 1 and 2. Fine. So now this is nothing but a geometric series in terms of n, you will see, and the ratio is lambda, magnitude of lambda into m into b minus a. This is free from n, so we are taking only terms which involving n. So that's why the corresponding series converges only when this ratio lambda n into m into b minus a is less than 1, because this is the geometric series, and this will converges when magnitude of this ratio is less than 1. So from here magnitude of lambda is less than 1 by m into b minus a, which holds, because, and this ratio holds. Why? Because we have already taken the assumption number 3. So series number 10 converges absolutely, uniformly, as per the Weierstrass theorem test. Absolutely means we have absolutely, and uniformly means we have used the Weierstrass M test. You have already, I think, understand what is the Weierstrass M test. So this series is absolutely and uniformly converges, and due to the condition number 3, due to this ratio. So the solution of 1 can be expressed as equation number 8. So we can express the equation, the solution in this form. In this form we can write down. Fine. Now here, now if yx is continuous, because here we have seen that this series is continuous. So since yx is continuous, then obviously its magnitude will be continuous. Fine. And bounded also. Yx must have a maximum, because this is continuous, its magnitude will be continuous, and then bounded also. So we can say that magnitude of yx is less than equal to some a. A is any arbitrary constant, a constant, because this is a continuous and bounded also, that's why. So then from ninth equation, this equation, this is the ninth equation. Take the magnitude of this. So magnitude of the remainder term, so magnitude of this, again following the same procedure, just like here. So here we are having magnitude of lambda n plus a, magnitude of kernel, how many kernels are there? Total m plus 1, because here n plus 1, so n plus 1, so magnitude of m n plus 1. After taking these this constant values outside the integral, we are having integral a to b, integral a to b, integral a to b, and then magnitude of yt and also taken outside, which is nothing but less than a. So this is a. तो केवल integrals बचेंगे. How many integrals are there? Total n plus 1. After solving these integrals, we are having a b minus a raised to the power n plus 1. And since this condition holds, that's why the ratio from here, this is also less than a. So we can say that as n tending to infinite, this will tend to 0, क्योंकि ये जो रेशो है वो लेस देन 1 होगा. So this will tending to 0 as n tending to infinite, and hence remainder term tending to 0. So इस सीरीज में this term tending to 0 as n tending to infinite, and that's why we are getting a solution in terms of series. So this is the solution. Fine. Now in the next video we will take this solution of Volterra integral equation of the second kind by successive substitution. So in this problem we have taken Fredholm integral equation. Now we will take Volterra integral equation with the help of substitution method. Fine. Okay, thank you.